Okay, in this next topic worksheet here, we're going to focus on section 5.2 to really the end of chapter 5. Of course, you guys have already been tested over 5.1, so that's why we're starting in 5.2 here now. 5.2 is all about inverse functions. Inverse just means that you're switching x and y. Problem 1, it says, is just some true-false. So part A, the function that's given there is a one-to-one function. Okay, one-to-one just means that the inverse is a function. You see, if you switch x and y, do you still have a function? Maybe or maybe not. You know, like for this problem here, if we switch the coordinates in this set, then we're going to have another set of points, which are 5, -7, 5, 2, and -3, -1. Okay, now 5 is going to two different y values. You can't have that with a function, so no, the inverse is not a function, therefore the original function is not one-to-one. Okay. Part B, the function f of x equal the absolute value of x minus 1 is a one-to-one function. No, that's false, because the horizontal line test is a test that you can use to determine if a function is one-to-one. Of course, if we had f of x equal the absolute value of x, we know we have a v-shaped graph centered at the origin, and the -1 means that I would shift that over to the right 1 unit. Okay, here would be the vertex right at 1. Yeah, so this function would fail the horizontal line test. If I swing a horizontal line down the graph, you know, it's going to intersect in more than one point there. So this function is not one-to-one. Okay, and what that means to us is that this function has an inverse, but that inverse is going to be some curve that would fail the vertical line test. Part C, the functions f and g are inverses of each other. That's going to be false. Two functions are inverses of each other if you plug each one into the other and you get just x. So if I plug g into f, g is given, that's 1/5 x plus 3. Plug that into f, there's only one x in f, so I've replaced that one x with 1/5 x plus 3. And if I then simplify, distribute the 5, so you'll have x plus 15 minus 3, that's x plus 12. Okay, so because I'm getting x plus 12 and not just plain old x, then I don't even have to bother checking g composed f of x. I already know that these two functions are not inverses of each other. By the way, it would be inverses if you had parentheses around the x plus 3. Okay, so we don't have that here, but if we did have the parentheses around the x plus 3, we would get just x by plugging each function into the other. Okay, so like any other math problem, you know, the notation matters, the parentheses would matter there. Problem 2, the graph of a one-to-one function is given. We want to draw the inverse on the same graph. Okay, the inverse is all about switching x and y. So in this picture here, I'm just going to switch the coordinates and plot the new points. -2, -2 is going to stay right at -2, -2. -1, 0 is going to be at 0, -1. And then 2.721 is going to be at 1, 2.72. Connect those 3 points with 2 straight lines there. And that curve that is in red would be the inverse of the function. Now, one-to-one means that the inverse is a function. Notice how the curve in red passes the vertical line test. Okay, and of course I could have known that early on here, you know, the curve that is in black passes the horizontal line test. So before I even drew this, I could have known that the answer, the inverse, would be a function. I've also got the line y equal x drawn. So whenever we have a graph of a function and its inverse on the same picture, those two curves are always going to be symmetric to the line y equal x. So I've got that there just so that we can see that these two graphs are symmetric about the line y equal x. That will always happen with a function and its inverse. Okay, problem 3. we want to compute the inverse of f of x equal x squared minus 7 and then state the domain and the range. Y and f of x mean the same thing, so I've rewritten this as an equation in terms of x and y, and then inverse means that it's all about switching x and y. So I've done that here in this equation, and now I'll have to solve this equation for y. Add 7 to both sides and then take the square root of both sides. Of course, don't forget about the plus or minus when you take the square root of both sides. And you have y equal plus or minus the square root of x plus 7 then as the inverse. Okay, now is the function 1 to 1? No. You see, 1 to 1 again just means that the inverse is a function. So here's the inverse that I've got circled. This is not a function, because for each x there's only one y, right? There's not a plus y and a minus y, there's only one y for each x. So I don't want to be using the inverse function notation. Sometimes that's going to be appropriate to do and sometimes not. I want to leave my answer in terms of y and x for this problem since the inverse is not a function. Find the domain and the range of f. Okay, f is a quadratic. The domain of any quadratic is all real numbers. We did lots of things with quadratics in Chapter 3. The range of the function, a couple of different ways that we can see this. One option would be to state the domain of the inverse. The range of a function is always going to be the same set of numbers as the domain of the inverse. Okay, so domain means I'm talking about x here. With what I have circled, what are the conditions on x? Well, I know that I want x plus 7 not to be a negative, since the square root of a negative is not a real number, it's an imaginary number, right? Solve that for x, and it looks like anything greater than or equal to negative 7 would be okay to use. Now, the only change on that is that you want to be using y, since you're talking about the range of f. But then notice how that's the same group of numbers there. Okay, the range of a function and the domain of the inverse will always be the same set of numbers. Now, another way to look at this is, you know, I know I'm drawing a parabola. We did lots of things with parabolas in Chapter 3. This is a quadratic. And this parabola would be shifted down 7 units, right? So on a graph, you would have, you know, the parabola and then be shifted down 7 units. Here would be the point 0, negative 7, okay, on the y-axis. And you can see that anything that is negative 7 or bigger is going to be in the range of the function there. It's going to put you on the graph. Problem 4, compute the inverse of f of x and then state the domain and the range. Okay, so we just have a different function here. Y and f of x mean the same thing, so I've rewritten this equation in terms of x and y, and then switch x and y since we're computing an inverse, and then we need to solve for y. Okay, if you multiply both sides by y minus 3, that'll get rid of the fractional form that's on the right. And on the left, you'll want to distribute x into y minus 3. You're going to have x times y minus 3 times x then on the left. We're solving for y, so I'd want to add 3x to both sides and then divide by x on both sides. Now, this function, the original one, is 1 to 1 because the inverse turned out to be a function. For each x, there's only one y. Like, I didn't have any plus-minus deal come up like I saw in the last problem. So in this problem, like, if I wanted to, I could use the inverse function notation. That would be fine. I could have also left my answer in terms of y and x. That would have been fine, too. Okay, but the point is that, you know, sometimes it's going to be okay to use this inverse function notation, and sometimes not. You just want to be careful about blindly using it all the time there. Some students will sometimes do that. All right, we want to find the domain and the range of f. Here's f of x. Of course, we can't divide by 0, right? So we don't want x to be 3. The range of the function is the same as the domain of the inverse. Okay, I've calculated the inverse, and I know I can't divide by 0. X is in the denominator, so just don't let x be 0. Of course, when I state the range, I want to be using the variable y and not x. Okay, but it's going to be the same set of numbers. Y can't be 0. Another way to look at it, just to kind of intertwine some other things that we've already talked about, f is a rational function. In section 4.6, in the 115 class, we did things with rational functions. Remember that when graphing a rational function, we got to pay attention to any asymptotes that are on the graph. This graph would have a horizontal asymptote at y equals 0. Since the degree of the top is 0 and the degree of the bottom is 1, anytime the degree of the top is less than the degree of the bottom, y equals 0 is going to be an asymptote. Okay, so the reason why we're throwing away 0 is because on this graph there would be a boundary there at y equals 0.